This video is going to be the first of a series on how we have indefinite integrals and what we can do in order to find integrals when that's the case. So this first type is when one of your bounds actually goes to infinity. So I want to remind us that a definite integral, you're finding the area between the function and the x-axis from a to b. Well, what happens when your b term is infinite? Okay, so if we look at like from a to some function t, where you're plugging in like different t values, and you can see like as we increase the value of t, we're increasing that area. But how do we find if we like let t essentially go to infinity? Like, can we add up all of that area? And this is a really crucial concept because our next big section is going to be on series, where we're going to have to figure out like if you have an infinite sum of something, can you actually find that sum, or is it infinite? So here's some definitions for us to look at. If you are going to have an integral from a real number to infinity, then we're going to change that to be the limit as t goes to infinity, and then change that bound. You can also do this from negative infinity to a number by doing this here. We call that an improper integral. And if that limit exists, if you find a real number, if you find a limit here, then we say that that limit or that improper integral converges. But if it doesn't exist, then we're going to say diverge. And those are two very important terms to know. Converge means that you have a number. Diverge means goes to infinity. It is also possible that if you wanted to do from negative infinity to infinity, as long as you are continuous on that interval, you can choose, here in the example it gives us 0, you can really choose anything. So you can choose from negative infinity to any distinct real number, and then that same number to infinity. So you just break up negative infinity to infinity. You just say like, okay, I'm going to choose this as my break and set that is two integrals. If they both converge, great. If either one diverge, you're out, okay? All right, so let's look at some of these, like a review question I have here for us to look at. For the integral of the volume of find the volume of the solid revolving the region of 1 over x from 1 to infinity. So let's again look at what that would look like. Okay, 1 over x from 1 to infinity, and I'm taking that region around the x-axis. And I mean, I'm going to end up having like this infinite funnel looking thing, like so. So let's remind ourselves our r is going to be our function value. So I'm going to take the integral from 1 to infinity of pi r squared, and each disk has a thickness of dx, and then I want to add all of those up. I'm going to take the pi out, as well as I'm going to change this to be, as the limit as t goes to infinity, 1 to t. I can take this pi all the way out here, actually, and then I have 1 over x squared dx. Well, that's the same thing as x to the negative 2, so I would have pi limit as t goes to infinity. X to the negative 2 would have the integral of negative 1 over x, over x. And I'm evaluating that from x equals 1 to t. Okay, leave the pi out here. Let's plug that in. Limit as t goes to infinity of negative 1 over t minus negative 1 over 1. Or plus 1, if you will. All right, now let's evaluate. As t goes to infinity, this guy here goes to 0. So I just get pi times 1. So that volume, y'all, is pi. And this is always an interesting concept to me, because I'm like, wait a second. Our funnel never stops. Our funnel never stops, but it has a volume. That's crazy, okay? This limit converges, this volume converges to pi, and we actually have a volume of this like infinite funnel. All right, let's look at example number 2. Example number 2, I want to evaluate from negative infinity to 0 of 1 over x squared plus 4. Does this improper integral converge or diverge? The function 1 over x squared plus 4, if you look at it, looks like this, where at 0, I'm at 1/4. And so I want to add up this area from negative infinity to 0. So we're going to say that's the limit as t goes to negative infinity of t to 0, 1 over x squared plus 4 dx. This is an antiderivative that we need to know. If you try to do u sub, you can't. If you try to do trigonometric substitution, you could, but you need to recognize that this is the derivative of an arctan function. So limit as t goes to negative infinity of, ends up being 1/2, because you do, like, this is 2 squared. So 1/2 arctan of x over 2 from t goes to negative infinity to 0. All right, so we will have the limit as t goes to negative infinity of 1/2, and then we'll plug in 0. Arctan of 0 minus arctan of t. All right, let's remind ourselves what the arctan function looks like. So this is 1 over x squared plus 4. The arctan function, as t goes to infinity and negative infinity, have horizontal asymptotes at negative pi over 2 down here and pi over 2 up here. So I'm going to go ahead and evaluate an arctan of 0 is 0. I'm going to take this 1/2 out because I can, and then I'm going to just be looking at the limit as t goes to negative infinity of the negative arctan of t. And if I evaluate that to negative infinity, this goes to negative pi over 2. Well, negative, negative, positive. So 1/2 times pi over 2, and my final answer is going to be pi over 4.